This is the solution for question 1a of homework 3. The first thing we need to do is to rewrite the equation in the form dy over dx plus p of x times y equals q of x. So when we write it in those terms, the equation becomes so as you notice, all we had to do is divide by x the whole equation. We're going to use Bernoulli's method. Of course, we can identify q of x with negative 1 over x and p of x and q of x with x cosine x. Using Bernoulli's method, we let y is equal to some u of x times v of x, and while differentiating, that's going to be u dv over dx plus v du over dx. So we're going to substitute that onto the equation. I'm gonna give it a number here. It's gonna be equation 1. So that becomes u dv over dx plus v du over dx minus 1 over x times y, which we said is u times v, and that is equal to x cosine x. The next thing we do is we factor out u. So that will be u times dv over dx minus 1 over x times v plus v du over dx equals x cosine x. So if we can find a function v that will make this identically 0, then our initial differential equation will be reduced greatly to just the terms that we have over here. So let's find that function v first. So I have dv over dx minus 1 over x times v equals to 0. Well, that implies that dv over dx is equal to v over x, which can be solved by separating the variables. And that gives me dv over v equals to dx over x, the integral. Integrating, we get natural log of v is equal to natural log of x plus the natural log of some constant. Using the properties of logs and taking the exponential on both sides, we get v is equal to c times x. So this function will fulfill the required property that this term is 0. So now we solve the other side. V du over dx equals x cosine x. V du over dx equals to x cosine x. And we had that v is actually equal to cx times du over dx is equal to x cosine x. So from there it follows that c du over dx is equal to cosine x. So we can find the antiderivative of this function, and we have that c times u is equal to sine x plus some other constant. I'll call that one b. So what do we have? I have that y is equal to u times v That means that y is equal to, here I'm gonna divide everything by c, so that gives me u is equal to some constant sine x, where a is equal to 1 over c plus k. So that's going to be a sine x plus k that multiplies v, that is c times x. Okay, so that is my solution. Now to check whether or not that is true, we differentiate, and we have a times c. I'm going to expand d over dx of a sine x plus k that multiplies cx plus a sine x plus k multiplies d over dx of cx, which simplifies to acx cosine x plus ac sine x plus some constant ck. So we can rename some of the constants, and that will be alpha x, and let's leave it like that for now. Let us see what the initial equation was. The initial equation says that x times y prime minus y is equal to x squared cosine x. So let's multiply this by x and subtract y. So xy prime minus y is equal to ac x squared cosine x plus acx sine x plus ckx minus y. So that means minus acx sine x and minus ckx. Now that cancels two of the terms, and we end up with acx squared cosine x. Now what is it that we needed? We needed x squared cosine x. Okay, so that means that this a times c deal is actually 1. Okay, because otherwise this would not really be a solution. Let's see, so that means that y is equal to acx sine x minus some ckx. So this ac was 1, therefore this x sine x, and I'm going to name this other constant alpha. And this is the solution to the differential equation.